I hope that everybody got a very joyful weekend. So it's for a week already, right? So let me share with you what we did last time to refresh our memories, and let's move on from there. So you can always check the class notes, right? This is the class notes from last time, right? We talk about what process. It is a series of activities for the flow units to go through, right? At the beginning, the flow units are the inputs, and at the end, they are the outputs. So after that, we talk about the three fundamental metrics that a process would have, any process would have, right? The inventory, the flow time, the flow rate. The inventory is how many units you still see within the process at any given time. It is called inventory, right? The flow time is how long it takes for one unit to go from the beginning to the end. And then the flow rate is how many units going through per time unit, per minute, per hour, per week, per month, per year, something like that, right? So yeah, for any process, we can measure these three fundamental metrics. And they are important because the inventory is related to the size of the business. And you need to make big decisions on your business, right? Expand it or something like that. Regarding the flow time, it reflects the total level or the effective level of technology that you have, right? So if you want to cut out the flow time, maybe you have to use better technology, you have to have more resources, right? And then total of flow rate, the revenue, it is related to your revenue and profit. And then that's why as a manager, we look at the flow rate all the time to track what is going on with our process. And if you need to ramp it up, then you have to do something about other metrics, right? So that's what we left off last time. Just some conceptual and basic discussion on a process evaluation, and the three fundamental metrics. And today we move on with the so-called Little's Law. The Little's Law is the law that ties the three fundamental metrics together, right? They are not loose anymore. They are tied together by the Little's Law. But remember, this Little's Law only works with the averages. So let me share with you the Little's Law, discuss that with you a little bit, and then we will go through a series of examples, and hopefully that will help you to make much more sense of the Little's Law. All right, so let me share the Little's Law with you. All right, so on slide 18 of module 3, right, we say that the average inventory equals the average flow rate times the average flow time. So we have three fundamental metrics, or three averages, or three average numbers, right? Then they are following this law. This law is proven mathematically, so it should be correct as long as we talk about the averages, right? And the law itself is named after Professor John D.C. Little. So the Little's Law is meaningful in the following sense. Sometimes it's very hard to measure one metric. So in that case, we measure the other two first, and then we can infer the third one based on this equation, right? Because in this equation, if we know two, then we can infer the third one. So it depends on the business situation. Sometimes it's very hard to measure the third metric. So in that case, you would measure the first two easy metrics. And all of those are depending on the situation, right? Like what is easy, what is hard. Then if you measure the first two, then you can easily infer or calculate the third one based on the Little's Law, okay? So later on, we're gonna go through these examples. This example on slide 20, one example on slide 21, another example on slide 22, and at the end, I'm gonna show you the ultimate example on slide 23 about the Little's Law. All right, so let's work on these three examples first. Let me give you the information here. So in the first example, we're going to talk about the U.S. immigration process, right? So the visa application goes in the process, and they give us the flow time, they give us the flow rate, and they ask for the inventory. Okay. In the second example, we talk about the champagne industry. They give us the inventory, they give us the flow rate, and we need to figure out the flow time. In the third example, in the tablet factory example, they give us the inventory, they give us the flow time, and we need to calculate the flow rate, right? So those are the three basic examples that we're gonna work on very shortly to make some sense of the Littlest Law. So let me go back to the whiteboard and work on this with you. So we're still in module 3 about process performance. So let me remind you that last time we already talked about the overview of process performance. In which we talk about the three fundamental process metrics, sorry, the three fundamental metrics. Inventory, flow time, and flow rate. And today we move on to the next big topic, the Littlest Law. Right? So in this case, on average, maybe it's too tight. The average inventory equals average flow rate times average flow time. Right, so that's the equation. And to make it more succinct, we're going to talk about the Little's Law as I equals R times T, right? Or I equals T times R. It doesn't matter which order it goes, because multiplication is commutative, which means that the order of operation doesn't matter. All right, so that's the Little's Law, right? On average, the three numbers will be tied together by this equation. And again, it is proven mathematically, so it should be correct if we talk about the average or the averages. Okay, so what is the meaning or the usage of the Little's Law? So a lot of the time, it is really hard to measure the third metric, right? So that's why we just kind of infer the third metric based on the first two. So one usage of the Little's Law is we can infer the third metric. Either I or RT, right? We infer either one of them based on the other two. And the second, also based on this equation, right? We can make predictions on the third metric or prediction on changes. Like if we know that during the holiday seasons, a lot of people will buy something, right? Then if you are at the FedEx, UPS, or the post office, we know that the flow rate will increase. And we want to maintain the flow time, then in that case, we're going to have more inventory. And when we have more inventory, and we want to keep the same flow time, right? Then you have to have more equipment. You had to have more trucks, more drivers, more warehouses, space, things like that, so that we can handle the bigger volume going through, right? Otherwise, we'll not be able to handle that. So, right, we can make the predictions and then we make our decisions accordingly. Okay, so even though the Littlest Law sounds little, right, but actually it's big. It's very big because it can be applied to any process, and then we can make predictions and then make our decisions, right, accordingly. All right, so that's the overview of the Littlest Law, and in this big topic, we're gonna go through a series of examples. So let's go through that slide 20 in the PowerPoint, and we have 3 examples over there. So the first example is the U.S. immigration process, right? The applicants will submit their visa application, and then USCIS, the government agency in charge of that matter, right, will look at the applications. So again, this is module 3, slide 20. First, to make more sense of the situation, let me draw the following diagram. So this is a U.S. immigration process, and the immigrants will submit their application. In the past, it's mostly paperwork application, but nowadays the paperwork are in the form of electronic like application, right? So it's much more convenient. Things happen faster. It's harder to make mistakes in the application process. All right, so they give us the following information. Again, I'm just looking at slide 20 right now. So they give us the flow time, 9 months, the flow rate of 6 million applications per year. So remember, we assume that the flow rate is the same at the beginning and the same at the end, right? So the same flow rate is 6 million applications per year. And this is an immigration process or visa application process, okay? So they give us the time, the flow rate, and they ask us how many or how many flow units in this case, or how many applications are still under review, are still under processing, right? And that's an inventory. So what is the inventory of this process? And to be more precise, right, we talk about the average inventory. At any point in time, on average, how many like paper or how many applications that we still have in the system. Still under review, not done yet, not decided on yet, okay? So remember, we have the Little's law, right? We need to find the inventory, so we just write that as I equals T times R, or R times T, it doesn't matter. So I would like you to try this equation. And remember, you should bring in the units, otherwise it might be wrong. So what would be the inventory in this application process? In other words, how many applications are still under review? So please try the Little's law equation and please share your answers in the chat window. Okay, so I got the first answer from Phelan and also from Christopher, right? Yeah, I don't say who is right or wrong. At least we have 2 camps here. Please go ahead and try. You know what? We are still learning. Right or wrong doesn't really matter. As long as you try it, that's good already, right? So please just try and see. All right. So yeah, Chillen changes the answer a little bit. What about other students? Please try the equation and share your thoughts on this. So just imagine the question asks us to see how many applications are still floating in the system, right? They are not done yet. All right. So I see from some of you, you have another number. Some,
Professor, the T is 9 million, right?
the T
Yes,
is 9 months.
9 months. Okay.
Yeah.
I see. So 9 times 6.
Yeah. 9 months.
I
But
see.
you should
That's per year.
the units, okay? Yeah, so I have a lot of contributions here already. Every day I see these contributions, I feel very happy about it. So it means that you are actively learning, and that's a very good thing. All right, so here's the thing. Now I see 2 camps, or might be 3 camps, right? So we need to kind of go through it systematically, so that at the end we have the correct answer, and in this case we only have 1 correct answer. Okay, so let me go through this with you. Again, we are still learning. So if you have something off, it doesn't matter. Okay, so let me go through this with you, and hopefully you see how to do this systematically. So the flow time is 9 months. So I would write out that as 9 months. Right? I don't change anything. The flow time is 9 months, so we just write out. The flow rate, they give us 6 million applications per year. So I also write it out as 6 million applications per year. Again, we do not change anything yet. But then now we see the months and the year, right? They do not work with each other. So we need to convert one into the other. And normally it's easier to convert the bigger one to the smaller one so that we don't have to deal with the fraction or the decimal number, right? So in this case, I will do the following. The 9 months, the same thing. Multiply with 6 million applications per year means per 12 months, right? We don't change anything. A year is 12 months. So now we have the same months on the top and at the bottom, they will cancel each other out. And that will help us to simplify the equation, right? So so just continue. Our I equals what? We have the months canceled out, so we have 9 times 6 divided by 12. And the million applications will be kept, right? Because it will not be canceled out. So million application. It doesn't hurt if you put the multiplication right there, times millions of applications. That's fine. Mathematically, that's correct. All right, but right now just call it as 9 times 6 divided by 12 million applications. Let's simplify this a little bit more. 6 divided by 12 is 1 divided by 2. And then you have 9 divided by 2, right? Then we have 4.5 million applications. So actually, all of you are on the right direction. It's just that this is the first time some of you might not pay much attention to the units. But hopefully from now on, right, in light of this kind of sequence, I hope that now you would know how to do it, right? When we talk about the time, then you have to write out the number and the time units. When we talk about the flow rate, you have to write out the number and then how many units per time unit, right? And then at the end, it's going to come out automatically correctly for you. So at the end, we have 4.5 and then million application. The million application is a built-in unit because you have all of the units along the way. So at the end, it has to be correct, right? Any question at this point? Yeah. So yeah, it doesn't matter if you get it off because we are still learning. So I totally understand. Anything for me to clarify at this point? So now we get it, right? On average, it means that if you look on the desk of the clock in the whole system or in the computer, if we can see it, then we have 4.5 million applications still under review. They are not done yet. They are still under processing. And after, on average, 9 months, right, then they will be kind of decided on. The 9 months here, remember, it is an average number. Some application takes more than 9 months. Some application take less than 9 months, right? But here we talk about the average of 9 months. And the 4.5 also on that's an average, right? On a particular day, we might have 4.5, another day 4.6, another day 4.4. But on average, it's going to be 4.5 application on our desk to be processed through. All right. So after we have the result like this, as a manager, we always have to think, okay, so we already have the number, what to do with it, okay? What comes next? So let me give you a situation here outside of the numbers that we have here, okay? So assume that you are the big boss at USCIS. You are working in Washington, DC. And then somebody give you this number. On average, we have 4.5 million applications on our desk. And you know that the number from last year is 4.0 million, okay? Last year is only 4.0 million applications, but this year on average, we're gonna have 4.5 million applications under review. So if you are the manager, what would you need to do to handle these 4.5 million applications so that we do not delay the process? We keep the same flow time, 9 months. Then what would you need to do to process this 4.5 million applications? Right. Last year is only 4 million, and this year is 4.5 million. Then as a manager, what would you do? What would you think of when you see this 4.5 million applications? Please feel free to share in the chat window, or you can discuss it with me. Okay, so I got the first feedback from Finland, right? Yeah, that's perfectly said. We need to hire more workers to process more applications. Otherwise, we're gonna pile up the inventory, and then the flow time will be very long. Yeah, but besides, remember, inventory is related to the size of the business, right? So the workers is the size of the business, but also is a whole host of other things that will be the size of the business. So let me give you some example about it. So we talk about the number of workers, but then you also have more office space, right? Of course, nowadays a lot of people works at home, but if you want it to be more secure, you ask your workers to go on site to work. Otherwise, how can you protect all of the communication, right? So office space, equipment, like computers, like a whole host of furnitures that you have to have, right? And then you have to have better software, better databases, or in general, we talk about information here. So that we can process a bigger inventory within the same time frame of 9 months, like before. Otherwise, we're going to pile up the inventory even more. Okay, so that's the way to go. During your calculation, please always keep the units, and then at the end, the final units will be kind of built-in unit is going to be correct, and you can easily make sense of the result, right? We have 4.5 million applications in our inventory, and then to handle that big inventory, you have to make the decision on the size of the business. And in this particular case, right, it's the number of workers and office space, equipment, computers, things like that, and then the information, the software side of the operations. All right, so that's the first basic example on slide 20. We have two more. So let me talk about the second example. Let's work on it together. So in the second example, we have the champagne industry or the champagne bottles. Module 3, slide 20. Okay, so let me draw the process here. Let's call this process as the champagne bottle distribution process. So let me make it short as bottle distribution. All right, so if you have a winery, think about it. How can you sell your champagne wide and far away? You cannot put that in the big container and sell that to a whole host of customers, right? You have to bottle it up. So at the beginning of the process, right here, the liquid is bottled up into the bottles. And then the bottles are floating through the distribution channels. And at the end, they get sold to the customers, right? So that's the process that we talk about. So at the beginning, the bottle goes in, champagne bottles go in. Right? Of course, they are the liquid. But at the start of the process, now the liquids are transformed into the bottles. So we just imagine that the bottles go in the process. And then at the end, the bottles get sold. So they exit the process, right? By the way, let me talk about this a little bit. When we think about like the Napa Valley area, right? We have big wineries over there. So we normally take it for granted that the wineries, they will bottle the champagne by themselves, right? But then remember, you have to invest in the assembly line, and then you do not use that much because you only do that from time to time. So normally the wineries will hire some bottling company to do that for them. Okay, so how do they do it? On that particular day, the bottling company will pull up a very big truck to the winery, and inside the truck it is the full assembly line right there, where they hook up the champagne, and then they already have the empty bottles in the cartridges, and then through the assembly line, right, they will bottle it up. Right, it's quite fast and very efficient. So the fees that they charge is not as much as if the wineries invest in the system, right, and do not use that much. All right, so we already have the bottle distribution process here. And in the slide, they give us the following information. So in terms of the inventory, we have 875 million bottles. Remember, we talk about the whole industry. It's not the whole Napa Valley areas, right? For example. So we have many wineries, and then they might have that in their warehouses, or they are on the truck to the distribution centers, and then possibly they are still in the warehouses or the back of the restaurants because they are not sold yet, right? So if we think about this as a very big, large distribution system, then we have 870 million bottles on average on any day, right? is a very big number because of that. We talk about the whole industry. All right. And then they also give us the flow rate. So remember, the flow rate is the same number here or here at the end. So we have 250 million bottles per year. Okay, so now we know the inventory, we know the flow rate, and obviously the question is asking us about the flow time, right? So yeah, Theo, please ask your question.
Professor, wouldn't it make sense for the companies to have their own bottling like process in the long run, as far as like?
So if they think that they can sell things very fast, they need that every week or something like that, then it makes sense to invest in that system. Otherwise, might be just hiring another company, and then you can save a lot of money by not investing in a big system like that. All right, so it depends. If you sell a lot, you need to do bottling every week, then possibly it makes sense to have your own system. All right. I know about this because one of my students told me the story. The wineries in the whole area, they only have 2 companies doing this. Why? Because they do not have to do that frequently, and if they invest a lot of money in that, then it does not make economic sense.
But also, there is only 2 companies, they can have a monopoly and just charge whatever they want, right?
Yeah, but you know what? They cannot charge too high, because if they charge it too high, then another company will jump in, because now they say a large profit margin, right? So that's why it is okay for the wineries to live with those 2 companies. So yeah, at least my student did not kind of tell me what area it is. Maybe it's here in Southern California, somewhere around here, possibly.
Thank you.
Yeah. Sure. So in this case, right? So we need to find the flow time. Please feel free to do the calculation and share your answer in the chat window. So the flow time. Remember that we just kind of rearrange the Littlest Law equation, right? Then the flow time is I divided by R. So please try it and share your results. Please, yeah, please feel free to share your results. By the way, like before, right? Please keep the units along your calculation.
The I is 875 million bottles per day, right?
No, I is just a number, a count number. It's not per day or anything.
I see.
Because it's like you look at the warehouse right now, you have an inventory of 1,000 bottles, right? It's not.
See. Gotcha.
Yeah. So this is an average number. Another day we might have like 870 million bottles. Another day is 880 million bottles, right? But on average over the day, then we have 875 million bottles on average. So what would be the flow time in this case? Yeah, just take your times and please share your answer. And at the end, it's interesting to know, right? How to have the flow time. You have to track millions and millions of bottles from the time it is bottled up to the time they get sold. And how can we do it? Whereas the bottles are exported to many other countries, many other cities. There's no way for us to track each of the bottle to calculate the average flow time, right? But then, based on the Littlest Law, now we can know how long it takes from the time of bottling up to the time of sales. So how long is that? All right, so at least I see something here. But somehow in the chat window, I do not see that. All right, so might be my Zoom is freezing a little bit. I did not see the updates on the chat window. So let me check one thing here. Oops, it doesn't allow me to check. You know what? From time to time, some might be the updates of Zoom or something. It blocks my. Oh, I did not see your.
All the answers are 3.5 years, Professor.
Oh, thank you so much. Thank you so much. And you are all correct. You know what? The chat window is gonna frozen right now. I cannot see any updates. I'm sorry about that. I don't know what happened. All right, later on I will deal with it. So the T is I divided by R. We take 875 million bottles divided by 250 million bottles per year. So the million bottles will be canceled out, right? And we only have a year left. Where does a year go? The year is in the denominator of another denominator. So it's going to be flipped up, right? So the next step is 875 divided by 250 year or years. So finally, our answer is 3.5 years, right? So it's interesting to know that, okay, even though we cannot trade millions of bottles, but if we can calculate the average flow time among million bottles, we're gonna have 3.5 years, okay? But then as a manager, right, we look at this number and we ask ourselves what to do with it. So remember, the champagne will need to stay in the big container in the cellar for some time. It ages a little bit already, right? And then it takes about 3.5 more years for it to age. So as a manager of the winery, you're gonna decide on what would be the perfect time or the best time to bottle the champagne up so that we have the time in the cellar and the 3.5 years on average. So when the bottle gets sold, it ages beautifully to be consumed, right? And the customer will like your champagne more and they will buy more from you. Remember, we bring more values and people will buy more from you, right? So remember, we always gotta calculate the numbers, but at the end we have to think about what to do with it. All right, so that's the second example. And here is the third example. Maybe this is just an example number. In Champagne, I don't think it's going to last it long. I'm not quite sure. I take this example from the book. But hopefully you make some sense of how to do the calculation and what to do with it, okay? So the next example also on slide 20. It is the tablet factory. So this is module 3 and also slide 20. So we have the assembly line where we assemble the tablets, right? From time to time, we hear about the iPad factory in China, right? So they will need to have the factory to do it. Okay, so this is our assembly line. So the tablets will go in and the tablets will go out. remember at the beginnings, right? We don't see the actual tablets yet. We only see the components, parts, assemblies, sub-assemblies, things like that, or the materials. But then remember, we can imagine with this amount, we're gonna build this one tablet, right? So with the total amount, we're gonna imagine how many tablets going in. And at the end, we have the actual tablets going in, right? This one is easy to count. All right, so we have the following. The question give us the inventory. The inventory here is 200,000 tablets. And they give us the flow time of 10 days. And they ask us for the flow rate. So what would be the flow rate of this process? Okay, so let's work on this together. So we know that the flow rate can be calculated as I divided by T, right? We just rearrange the Little's law because the three numbers are tied together. So I divided by T. And then I is, I believe that all of you can do this. That's why I work on this with you to save some time, okay? So we have 200,000 tablets. That's an inventory, right? We know the number, but we also have to write out the unit. Divided by 10 days. So at the end, the R will be the following. The tablets and the days, they will stay because there's no way for us to cancel them out, right? So we only do the number here, and we at the end we have 20,000. And then tablets, we keep that units divided by day or per day when we call in the daily language, right? So the flow rate every day is 20,000 tablets. So as a manager, you track this number very closely because it is related to our revenue stream or the profit stream, okay? If the number is going up, you're happy about it. If it is going down, for example, because of the shortage in the computer chips, maybe we do not have enough chips to put in the assembly line to maintain this 20,000 volume every day, right? Then you're not happy about it because your revenue will go down and you have to find some way to back it up, right? To find some source of chip, whatever it takes, so that you can maintain your flow rate. By the way, last week I heard the news that GM will need to close several factories because they don't have the computer chips to put in the cars. So they only focus on the cars that makes the most money, right? So we are facing that kind of shortages right now, and that will slow down the flows, okay? Because the inputs going in, going down, so the going out will be lower than before. All right, so these are the three basic examples of how the Little's law works. Does anybody have a question for me at this point? Anything that I need to clarify with you? Are you good so far? Okay, you know what? I'm not quite sure. Might be the chat window is frozen, is still frozen. Okay, so in the next part, I'm gonna show you the next example. The next example is more demanding than what we just have because those are the word problems, right? It's like you are reading a story and then you have to read out the information from the story, right? So it's gonna be a little bit more demanding, more confusing than what we just did. So let me share what. Let me make sure that I save this one first. Okay. Hopefully I go back to the chart and then I can see things. So let me share the next example with you on slide 21. Okay, a large-scale bakery is laying out a new production process for its packaged bread. Oh, by the way, let's keep the first one, the example on the top, because it's very similar to what you read in the book. So let's work on the second. A large-scale bakery is laying out a new production process for its packaged bread, which it sells to several grocery chains. It takes 12 minutes to bake the bread. How large of an oven is required so that the company is able to produce 4,200 units of bread per hour, measured in the number of units that can be baked simultaneously. Okay, so in this case, right, as a manager, you are thinking about a new process, and you need to design it, right, to meet your business needs. So it's like we're reading a story, and we need to parse it. We need to extract the information from the story, right, for our calculation. So I would like to ask the whole class, when you read here, it takes 12 minutes to bake the bread. What is that information? Is that inventory? Is that flow time, or is that flow rate? Please feel free to share in the chat window. Later on, I think that I can manage and retrieve your chat entry. All right, I see that from Trillian. Alita also flow time, yeah. And CPay also flow time. Oh, the rate? Oh, it should be flow time, right? Because we talk about 12 minutes. So the 12 minutes is the time that the doughs stay in the oven. So we should understand that 12 minutes as the flow time of the process, right? So I hope that now you see that as a flow time. How about the next piece of information? To produce 4,200 units of bread per hour. So what is that this time? Is that inventory? Is that flow time, or is that flow rate? We always talk about the three metrics, right? So 4,200 is what? I got it from Elita, Belen, Rosie, right? I have the second device, so at least I can see something going on. But the first device, for some reason, I do not get it from the chat window. All right, you are right. The 4,200 is flow rate, right? The number of units per hour, the unit itself already provides us the clue that it is a flow rate, right? So in this question, okay, is the story might be long, but now we already extracted two pieces of information. One is a flow time, the other is a flow rate. So technically, the question should ask us about the inventory, right? Right. But then let's look at the question: how large of an oven is required? Okay, is that about the inventory or not about the inventory? Do you think that the question is asking us about the inventory or no? It is a word problem. So, all right, fill and say inventory. In what sense? How large of an oven is? In the wording itself, we don't see any inventory, right? So that's why another student saying say no. Davida say no. Yeah, because you know what, it is a word problem. So sometimes I agree, it's confusing. It's not that straightforward. They ask about the size of the oven, how large of an oven is, right? But remember, last time when we talk about the inventory, we said that the inventory is closely related to the size of the business. And in this particular case, we talk about the size of the oven, right? That's why they ask how large of an oven is. So actually, they indirectly ask about the inventory by asking us about the size of the oven. Because if the oven is larger, then we can house more inventory. So after 12 minutes, we're gonna crank out more finished bread units, right? So that's why they ask us for the how large the oven is. So it's an indirect question about the inventory. Okay, so let's work on this. Again, let me go back to the whiteboard. So we have the following information. Example, this is our bakery process, right? Module 3, slide 21. So we have a process like this, where at the heart of that process, we have the oven. We don't have the oven yet, actually. We are only thinking about buying an oven. That's why the question answers how large the oven is. You have to make the decision on how large it is, right? All right, so remember the flow units here are the bread units. At the beginning, we don't have the fully cooked, fully baked good yet, right? We only have the doughs. They are raw. We cannot eat it. But through the hot oven for 12 minutes, at the end we have the fully baked goods, and then they are ready to be distributed and consumed, right? So bread units. But for process analysis, we have to say the same thing going in and the same thing going out. We have to have the consistency from the beginning to the end. So we say that the bread units go inside the process, and at the end, they exit the process. All right, so based on the information given by the question, we know that the flow time is 12 minutes. Right. If I miss any chat entry, then please bear with me, and if you can say it, then I will know. Otherwise, I will miss it. Anybody? If you want to ask me, please say it. All right. But because my second device is still working, so let me work on this first. So the flow time is 12 minutes, and they give us the flow rate, right? Remember, the flow rate is a constant flow rate. So we talk about 4,200 units per hour. Okay, and then so now we are supposed to find the inventory, right? We will fill the oven to the capacity, and that's why we want to know the size of the oven, because with that we will know how many bread units can be housed inside the oven. All right, so please work on this and please share your answer. So in this case, we need to find the inventory, right? So please go ahead with that equation right here, and then share your answer in the chat window. At least based on the second device, I can see the answer now. All right, so I have Phelan, Christopher, Elita. How about other students? What is the answer that you got? Christopher, so you all kind of agree with each other, right? All right, so that's a very good thing. You agree, and you are correct. So let me work on this with you. So we know that the flow time is 12 minutes. Right, and then the flow rate is 4,200 units per hour. So I just rewrite the information here without any changes, right? We don't want to change anything yet because we want to keep them original for it to be correct. All right, so we have the hour down here. But then we have the minutes and the hour. To make it easy, right? We're gonna convert the hours to the minutes. So we're gonna have 12 minutes. Again, we do not want to change it along the way because we want to do something else first. So 4,200 units. If you have the same number, please feel free to share. That's a record of your contribution. It doesn't matter right or wrong. Please just share. So the hour here is what? We have 60 minutes. All right. So the minutes and the minutes will be canceled out. We have 42. All right. So I also have that from Julian. That's good. So let's continue. Our inventory is going to be. So I would have the following. Okay. The minutes will be canceled out. We're going to have 12 divided by 60 times with 4,200 units, right? I do this because I know that 12 divided by 60 is going to be 1 divided by 5. And then we take 4,200 divided by 5, then you would have 840 bread units, right? That's the inventory. But that also tells us that that is how large the oven is, right? The oven has to be big enough to house 840 units at the same time, so that after 12 minutes, the 840 units will come out after every 12 minutes, right? And then you multiply that by 5, then you have 4,200 units per hour. You see the logic here, right? All right, so, but then as a manager, we do not stop here. We know now that the oven has to contain 840 bread units at any given time. So here's a question, my question for all of you, and it is gotta be on the information given by the question, okay? So in this case, doesn't mean that, does it? Does the result mean that we should buy a very large oven, very wide, very deep oven, so that we can house 840 bread units at the same time? So that's my question, okay? Should we buy a very large oven so that we can house 840 units simultaneously? Please feel free to share in the chat window. So should we buy a very large oven to do the task? It's beyond the information in the question. Adjust the question first to kind of learn how to manage, learn how to make decision here. Right. All right. So the answer is not quite obvious. So I got the first answer from Julian. You say yes, Julian. I hope that you just say that we would need to have an oven of 840 units. Okay. In that sense, your answer is correct. But then the answer is we should not buy a very wide and deep, very large oven like that. And here's the reason. If we buy a very large oven, then we have to have a big room. Think about 840 bread units. If it is a French bread style unit, it's going to be the size of a water bottle like this, right? And 840 is a very big number. So you have to have a very big room to house that oven. And it costs you a lot of space, and it costs you a lot of money to rent out the space. In the downtown area, it costs a lot of money to rent out 1 square foot. And now you have to have the whole room for that oven, it costs a lot of money, right? Think about it that way. So that's why we should not think about buying a very large oven. Instead, we buy a tall oven where we have different layers, we have different trays, so that we can cut down the space. For example, with the 840 units like this, cut about 7 trays, okay? 840 divided by 7 trays, then we have 120 units on each tray. Then it's not too bad, okay? Even though it's still big. If you want to cut it down, you have to do even smaller so that you can cut down the units on each of the tray. And you stack it up very tall like this, right? And you can save a lot of money in terms of the space cost. I hope you see that, right? So that's why when you walk in the Home Depot, walk in Lowe's, and some other kind of warehouse-like store, you see how high they stack the things up, because they still want to carry a lot of inventory, but at the same time they want to cut down the space, so they stack it very high. And of course, with that, they have to invest in the lift equipment, right? Otherwise, how can they retrieve it? Or in the Amazon warehouses or distribution centers, they also have to stack it very high to save on the space. Okay, so one trick that we learned here from this example is in operation. Sometimes we stack it up high so that we can save on the space. If we look at the container ships, the mega tons container ships, right? You know how high it is when we stack up the containers, right? A lot of things are stacking up. You look at the big trucks, the 18-wheelers every day on the road, you see it is higher than it is wide because of that reason too. Okay, on the street, on the road, you don't have too much space, so you can cut out the space by doing it taller. All right, so that's one way to go in operation, and please keep that in mind. All right, so that's the bakery example. We have another quick example here that I would like to work with you, so that I can show you the next example. All right, so we have another example on slide 22. Unfortunately, I cannot show that to you. So let me read the information for you. So the example here is about a baggage checking process. Okay, it is on slide 22. So consider the baggage check-in process of a small airline. Check-in data indicate that from 9 a.m. to 10 a.m., 240 passengers checked in. Okay, that's the first piece of information. Moreover, based on counting the number of passengers waiting in line, airport management found that the average number of passengers waiting for check-in was 30. Another piece of information, okay? How long did the average passenger have to wait in line? So if you draw the picture, then it's going to be the following. This is a process, and that's the check-in process, right? Airline check-in. I think that all of us already experienced that. So at the beginning, the passengers were walking the line. In aviation, we make this. They call the passengers as a tax to make it short. Okay. So the passengers will walk in, and at the end they will walk out of the line, right, after they already complete the check-in. So the passengers are the flow units of this process. They walk in, stay in the line, meet the associate, check the baggages, the baggage, and then at the end they walk out. Right? So that's the process that we talk about. So they give us some information here. From 9 a.m. to 10 a.m., which is 1 hour, they have 240 passengers through. So in that case, right, the flow rate is given to be 240 passengers per hour. The next, they say that on average, the number of passengers waiting for check-in was 30. So the inventory is 30 passengers. Okay. So by now we already know the inventory. We know the flow rate. And the question is supposed to ask us about the flow time. And actually it does. Okay. So how long did the average passenger have to wait in line? And they say here average passenger or typical passenger, right? Because remember, the Littlest Law only work with the averages. So that's why we only have the averages here. So on average, how long a passenger will have to wait in the line? So it's not difficult. The flow time, again, if we are using the Little's law, will be I divided by R. I is 30 passengers, right? And then R is 240 passengers per hour. So the passengers will be canceled out, the units will be canceled out, right? So we only have 30 divided by 240, and then the hour will be flipped up because hour is in the denominator of another denominator, right? So at the end, we have the following. So 30 divided by 240 is what? The zero will disappear. We only have 3 divided by 24. 3 divided by 24 is 1/8, right? So the flow time that we have here is going to be 1 hour divided by 8, right? So 8 here is just a simplification of 30 divided by 240. Okay, so that's why I have it like this. But then what is 1/8 of 1 hour? Can you make sense of that? If you divide that, then you have 0.125 of an hour. It's even more confusing, right? So that's why we would like to convert it to the minutes. And it makes more sense to talk about the minutes, right? So instead of 1 hour, we talk about 60 minutes divided by 8. And at the end, the answer is 7.5 minutes. So it means that on average, a customer will have to stay in line for about 7.5 minutes. They walk in, and after 7.5 minutes, they walk out. Okay? Then it doesn't sound bad at all, right? Relative to our experience at the airports around here. We have to stay much longer than this. But if you are the manager of the airline and if you want to cut that time even further down so that you can satisfy, you can compete more with your competitors, right? Then in that case, you have to put more like a machine checkout, or you hire more employees to help out with the check-in process, right? Then you can cut the 7.5 minutes down to maybe 6 minutes or 5 minutes, right? And then people will be very happy with your services, right? So that's another quick example for us to learn about the Little's Law. And hopefully you can see that along the way during the calculation, you always have to keep the units, right? When we talk about the inventory, it is how many units, not just how many, right? Or the flow rate, how many units per time unit, per hour or something. Or the flow time, how many minutes it is, how many hours it is, right? So we have to be conscious about the units and then put all of them in, keep them in our calculation. And at the end, the units will be built in, will be coming out automatically. And then you have the correct answer with the correct units, and then you can make a lot of sense with the answer at the end, okay? And after we have the result, and as a manager, you need to make the next decision based on the results, right? So that's what we try to learn here. So we are done with this example. And I would like to show you the alternate example of the Little's Law. So let me try to share with you the next example. All right, it's a little bit tricky now because my Zoom is kind of frozen. Just give me just a little bit time here. Okay, so I think that we are going back. Okay. So let me share with you the slide. Recently, Zoom has an update. Might be because of problems. Not that sure. In my previous class, it's okay, but the second class always also problem. All right, so this is an ultimate example that I would like to show you. This is a bank visit process. Okay, so it's like you are looking at the lobby of a bank, and then you see the customer coming in, coming out. Right, so that's the bank visit process. So in this example, we have the timestamps of 10 customers who visited a local bank branch from 9 a.m. to 10 a.m. Right. So during that 1 hour time window, we see 10 customers walking in, and then they walked out at the end. So here are the information. Here's the information. Just bear with me. Can do it. All right. So in this case, right, what we see is the following. Customer one stayed from walked in at 9:01 and walked out at 9:07. Customer 2, 9:06, and walked out at 9:21. All right, I got a question from the chat window. Oh, anything? All right, it's not for me, right? All right, so in this example, we see the time in and time out, right? Customer 1 in at 9:01, out at 9:07. Customer 2, 9:06, and walked out at 9:21. Customer 3 in 9:08 and out at 9:20, right? So we have 10 customers. It's like you are looking at the security camera of the bank lobby area, right? Then you're gonna see these 10 customers walking in, walking out. You know exactly when they are in, they are out, right? And here are the two tasks of the exercise. First of all, we need to manually calculate the three metrics independently, which means that we cannot use a Little's Law. We have to calculate the inventory by itself, the flow rate by itself, the flow time by itself, based on their concept, right? Based on their definitions. Okay. So after we have the three metrics or the three numbers, right? We plug in the Little's Law and see if we have the equality or not. So those are the two tasks of the example. One is we calculate the three metrics independently, and second, we check if the three numbers, right, fit with the Little's Law equation or not. So you know what? Let's start with the easy metric first. You can easily do the flow rate, right? We know that in 1 hour we have 10 customers. So the flow rate here is easy. 10 customers per hour is very easy. So we already have the flow rate. And then the next easy metric would be the flow time. It's not too difficult. When we talk about the metrics in the Little's Law, we talk about the averages. So we have to calculate the average flow time, right? So we can easily calculate the flow time of customer 1, 2, all the way to 10, and take the average over 10 numbers, right? Then we have the average flow time. Of course, we're going to discuss in more detail next time. And then next Monday, we also try to calculate the inventory. Okay, so it's a very demanding example. We work on this next Monday. So have a great weekend. Have a great rest of your day, and then I'm gonna see you back next week. So if you have any questions, please feel free to ask me. Okay, otherwise, thank you, and I'll see you back next week.
Thank you, Professor.